Okay, so where we're at then today, for the like 8th time here, oh my gosh, was that we figured out that our initial position was this number. All right? Okay. So we figured out the period, right, by measuring the time from peak to peak. We inverted that to find the frequency. We found our angular frequency, which was this. And remind me in a minute to show you something that'll help you that Patrick shared that I think will help you get a better understanding for what this is. We used the data from the table to figure out our minimum and maximum position, and then found our, maximum amplitude, I guess, is what that would be called. And we came up with this expression. All right, so we decided that our position at time t was equal to our maximum displacement times the cosine of angular frequency times time plus phi, right? Everybody good up to there? All right, and so, yeah.
I just, the 2xm equals the xo, that's the bit where I was...
Okay. Oh wait, 2xm does not equal xo. So the reason I'm hesitating is that I'm trying to decide if it's even worth going into because it's not going to come up again.
Just with scaling?
It's so here. So our xm was some number up here, right? Or I shouldn't call that xm. Our x max was, whatever this number was, 0.4 or something, right? And our x min was some number down here, right? Okay. Now what we want to do, so that's on this scale, right? But what we want to do is we want to create a new scale where this equilibrium point is an x of 0. Cool? So what I did was I subtracted my x max from my x min. Cool. So that was this, 0.2582, excuse me. So if you subtract your x max from your x min, you get this 0.2582. Okay, but that's the whole oscillation from top to bottom. What I'm really interested in is that distance. Good. So I chopped that in half, and that's where I got the 0.1, whatever it was, 291, I think. I did that in my head, so that might not be right, but cool. All right. So that's our x max. Okay. So what we need to do is we need to find the corresponding XO, not on the green scale, but on the blue scale. And so basically what that meant was that I had to shift everything down, by whatever this position is. Did that make a little bit of sense or no?
Yeah.
Okay.
I just thought when you had done the x max minus min, I think you might have said it's like x naught or something, and I got confused, but yeah, I get that it's like the distance between them.
Okay. All right. Are we good, you guys? I apologize for not. I'm hesitating because I'm trying to decide if we should go back and redo it again where I zero it out, but I think that's more work than we need to go into. All right. So anyway, so long story short, and I know it's too late. So we figure out our x naught on our new scale, and our x naught ends up being negative whatever that difference is. And it turns out to be negative 0.0739 meters. That's our minimum, that's our beginning position. Cool? So when I clicked collect, what this is telling me is that my mass was this far below the equilibrium position. That's what that number is telling us. Good? All right. And so what I charged you guys with was I said, figure out what that is, and then use that to calculate phi. And that was where we stopped.
Yes.
All right. So were you guys able to calculate phi? So what did we get? Sure, go ahead. What do you have?
No, I don't want to.
Oh, all right.
No. I got negative 3.18.
3.18?
2.
2.18. Okay. I think you guys have the same thing, but you're in degrees, you're in radians.
Oh.
Okay? I think. I don't know. Try converting 124 to radians and see what you get. Kelly, what did you say?
I got 2.18 radians.
Did a lot of people get 2.18? Anybody? Oh, let's see what Francis got. Did anybody? Francis, what did you get? 124?
Yeah, but
And-
let's do it if my calculations are radians.
So did anybody else get 124 degrees? Anybody get something different than one of those two things?
Yeah, that's 120.
Okay, cool. So you guys agreed, just different units. Hooray, cool. So we're in agreement. We do need to use radians though, because this are angular frequencies in radians. So you do need to use radians. All right, so everybody good up to there. All right, so it turns out to be 2.18 radians, but we need to check the sign. All right? I think that your calculator will give you a positive. Your calculator will give you a positive. Please hear me say this. Don't trust your calculator. It's a stinking lying. I insert mean word. All right? All right? You've got to check the sign yourself. So I don't know if you guys remember. Probably not, because it's been a couple days. And when we did this, I said, let's do an example. We can easily find the period of an oscillating object. So if we know XO and its direction of motion at that time, then we can derive the equation for the position. All right? So check it out. Here's what cosine of t looks like, right? Okay? Our graph looks like this. So to get our graph from this graph, which way do I need to shift it? I got to shift it to the right, don't I? Okay? Which means, do I want to do minus my phi value or plus my phi value? Minus. Okay? So, final answer then is, final answer is my board needs to be recalibrated. So here's my final answer. My position at time t is 0.1291 times the cosine of 3.85 t minus 2.18. Alex, did your calculator give you the negative?
No, I
Okay.
popped it out.
Okay. Does that make sense, you guys? Now, here's another way you could get to that result. If you're not sure which way to shift it, here's my recommendation, is this. And it took me a little while to kind of come up with the easiest way of explaining this. Our initial velocity needs to be positive, right? How do I know that? Because it's sloped uphill, right? So, if cosine looks like the green one, which way do I have to shift it to get it sloping uphill? Right? You got to shift it to the right, okay? And so that means that it's got to be minus, right? Because minus means shifting to the right, plus it means shifting to the left. Follow? Okay, cool. So, hooray! We just came up with an expression. Where'd it go? We just came up with an expression for our position at time t. So here's our expression for position at time t. We should check it. You guys all have graphing calculators, right? Let's graph it and see what we get. I'm going to use, on the interwebs, there is a graphing app called Desmos, which I enjoy. Here we go, Desmos graphing calculator. So here we go. So I want 0.291, no, 1291, sorry. Oops. Times the cosine of 3.85, I got to use x here, and then minus 2.18. There we go. Now let's scale it. My x-axis, I don't need the negatives on. We can probably just do, I don't know, 4 seconds. And then my y-axis, well, my max and min are 0.129, right? So let's just call this 0.15, oh, negative, and positive 0.15. Oops. Thank you for your patience, 0.15. Why does it hate me? 0.15. Oh, because I see, the negative didn't take, that's why. There we go. 0.15. Good enough. And there's our graph. Does that look like what it should look like? Hooray! Cool? Particularly when you're starting, you guys, that phi is going to be a pain in the... That's the thing that I struggle with the most, is figuring out what that phi is supposed to be. There have been a couple times when I've had it shift the wrong way, and it took me a little while to wrap my head around why. So my recommendation is once you come up with your function, graph it on your graphing calculator and see if it looks like, you know, what you think it's supposed to look like. Okay? Cool? All right, excelente. So that was a lot of work. Now, you can probably guess where we're going from here. So now we've got our equation for position at a given time. How are we going to find velocity at a given time? Take a derivative, right? How are we going to find the acceleration at a given time? Take a derivative, right? So really quickly, what's the derivative of cosine? Negative sine, right? And then the derivative of negative sine is negative cosine, right? So here are, I'm going to not go through the calculus because I think you guys can do that. Oh, well, I'll come back to that. So here are the expressions you get. So here's our position equation. Velocity, notice because of the chain rule, when you take this derivative, you got to pull your omega out. Okay? What's wrong? All right. So does anybody need me to say more about how I got these? Just by taking derivatives. Cool? All right. Now, notice that what's the maximum value sine can take on? 1, right? So my maximum velocity is going to be this mass times 1, right? So this is very important. I find myself using this a lot. Your maximum velocity is just omega times your maximum position. That's not at all obvious, but it's very useful. Okay, let me say that again. This is very important. Your maximum velocity, the maximum velocity achieved by your oscillating thing, is always equal to omega, whatever your angular frequency is, times xm. Yeah.
Why isn't acceleration omega squared?
Why isn't it?
Yeah.
It is.
I mean, in the note, like down, where you were just at.
Here?
Yeah.
Oh, it should be. It totally should be. That's a typo. Yep. Yep, you're right. You are 100% right. Yeah, so, and by the same logic, I would have caught that in like 2 more seconds. By the same logic, the maximum acceleration is omega squared times xm. Thank you. Yes?
Not into negative.
We're just talking about the magnitude, yeah. Yeah, I mean, so the idea is it's going to oscillate between positive this value and negative that value. Good? All right, so if you go back and look at the graphs, so here's our position graph, right? Here is our position graph, and there's our velocity graph. And notice it's just shifted by pi over 2 radians, which is how you get from cosine to sine, right? So it looks exactly the way you would expect it to. All right. What would the acceleration graph look like? It should look like the negative of the position graph, right? Right, because it's negative omega squared times xm, right? Okay, so let's do that. Let's do insert graph. There's my acceleration graph. cooperate with me. There we go. And there it is, basically the inverse of our position graph, right?
Yep.
Cool. Cool. All right. So I don't know if you guys noticed the little step I did here. So this mess here, oops, notice that this mess here is just our position at time t, isn't it? Okay? So that means that our acceleration, at any given instant, our acceleration can be written as the position at that same time multiplied by negative omega squared. Yes?
This is in meters per second squared, right?
Everything here is standard
Okay.
standard units, yep, and radians for angles, which is a drag, but what it is. Cool? All right, yes?
Where square neck goes up and down to fit at the maximum velocity.
That's the next thing I'm going to talk about. So,
Talk about it.
I talked about how to calculate it.
Oh,
I'm going to go back and talk about where it occurs in a second. Because they're not at the same instant, and that's an important thing. So hang tight for 1 second. All right. So we've got an equation for acceleration, right? Okay. So by multiplying acceleration by mass, we get force, right? Force is mass times acceleration, right? Newton's second law. So that means that our force at a given time is our acceleration at that time times the mass, right? Cool? Now notice, I don't know if you guys remember, one of the things we learned with simple harmonic motion, like the definition of simple harmonic motion, is it's motion in which the restoring force is proportional to the displacement. That's the definition, okay? The restoring force is proportional to the displacement. Now, remember you guys, our omega is a constant, right? And our mass is a constant. So if I write k as m times omega squared, then we get our force at a given time is negative some constant times the position at time t. So this is simple harmonic motion because now my force is proportional to the displacement.
okay.
Yeah, right here. It's k, it's m times omega squared.
Oh.
Oh,
Oh, yeah, that's a lowercase k. You guys remember Hooke's law?
Yeah.
F equals negative kx. Ah, F equals negative kx. Here's how you find out what k is. I don't know if that was a sincere oh, but all right, are we good? All right, so let me do one quick calculation, and then I want to take a step back, rewind, and hit Patrick's question, and sort of make sure you guys understand sort of how these graphs relate to each other and why it should make sense. Okay? So for us, let's figure out what k is. So k is, let's see, it's mass times omega squared. So for us, the mass on that thing is 0.2 kilograms. So let's see, for us, mass is 0.2 kilograms. And our omega was, what was it, 3.85?
Yes.
Radians per second squared. So that means that k is m times omega squared. So m times omega squared. So that's 0.2 kilograms times, oh shoot, my units on my omega are wrong. Omega is just radians per second, not radians per second squared. Sorry about that. 3.85 radians per second. Don't forget to square it. Let's see what that gives us. What is it? 2.96. Really? Am I skeptical about that? Oh yeah, that makes sense. Okay, sorry. Okay. Okay, any problems up to there? Okay. And then my units, because it's K, ought to be newtons per meter, which is not obvious, but remember, a newton is a kilogram meter squared. No, it's a kilogram meter per second squared, right? So when you divide by meters, you get kilograms per second squared. That comes down to, you remember how before we were multiplying by r, and it was like a conversion that converted to from the distance you traveled around your perimeter to a radian? So it's one of those things. Wizardry is going to be my horrible answer. Let's see if we can figure.
I think you would step out of that one.
Yeah. Well, I mean, there's an important reason why, but you'd have to do some digging to find it. It's got to come out in here somewhere. This x times omega. Yeah. Okay. Oh gosh, this board is driving me nuts. All right. So we ought to be able to test this, right? Okay. So let's do this. Unstretched. This thing's been hanging here for a long time, so it hasn't messed us up too much. All right. So with no mass hanging on this thing, it is more than a meter. All right, so right now, the bottom of this thing is about 1.3 meters above the floor. Okay? So somebody remember that number? 1.03. 1.03. Sorry about that. All right, so now I just applied a force to it, and it's stretched, right? And so now it is about, well, I got to measure to the end of the spring, not the end of the mass. So I'm going to call it 0.41. So here's what we just had. We have a force. How much force is that 0.2 kilograms exerting, or how would we find it? 0.2 kilograms times 9.8 meters a second squared gives us 1.96 newtons. And that gave us a stretch of, we went from 1.03 to 0.41. So what is that? Is it 0.062?
Yep.
Or 0.62 rather? I wonder what this will give us. So F equals Kx, right? I guess technically there's a negative sign in there, right? My force is down. So K equals negative F over X. So what's 1.96 over 0.62?
3.16.
So pretty close, right? We had two, so we're both right around 3. Cool. What'd you say, 3.16?
Yep.
Cool. And, you know, considering we did our calculations pretty quickly, not too bad. Questions, you guys? All right, cool. So here's the next sort of level of thing that we need to make sure that, whoa, let me talk about the omega thing real quick. So remember, the way I described omega was this. I said that, so your oscillation is going to go, you know, the thing is going to go down and up with some frequency, right? It's going to complete some number of cycles per second, right? And then I said, to think about angular frequency, you need to think about taking that one oscillation and dividing it up into 2 pi radians. Okay? Equating one cycle to 2 pi radians. And then Patrick was unsatisfied with that answer, as well he should have been. And he Googled, what did you Google again? You did simple harmonic motion, right? On the Wikipedia, and he found this little visual, which simplifies it. So the idea is our object is oscillating down and up. So that's in real space, right? That thing is oscillating up and down. And then if you equate that oscillation to 2 pi radians, you can see the little, little dot going around and around at the same frequency, right? So I don't know if that helps give you a little bit of a visual for what's going on. Make sense? No, but I mean, I think your point is important, that at any given instant, both green dots are at the same height, because that's what we're measuring, right? Are we good, you guys? Okay, cool. So I guess the next thing that I want to do is I want to make sure you guys understand kind of at what point does the maximum velocity occur? At what point does the maximum force occur? At what point does the maximum position occur? all of this stuff. All right. So maximum position is easy, right? Where does the maximum position occur? It occurs twice. At the top and the bottom, right? Technically, it's negative at the bottom and positive at the top, but those are the maximum positions, right? Now, remembering that force is proportional to displacement, when does your maximum force occur? At those same spots, right? More displacement means more force. The more I stretch my spring, the more restoring force it's exerting, right? Okay? All right, so far, at the top and the bottom, so this is our maximum position, it's our maximum force. Where would our maximum acceleration be? At that same place, right? Because your acceleration is proportional to your force. So that one position, and then similarly down here at the bottom, you're going to achieve those again, right? All right? Now, the signs are different though, right? So when you're at the top, point for me. What direction would my displacement vector point in? At the top, what direction would the displacement vector point in? Remember, you're measuring from equilibrium. So the displacement vector is going to point up at the top. What direction is the force from the spring pushing? Down. So what direction is your acceleration? Down, right? Everybody good with that? All right. Now, at what point do you think the velocity is the biggest? In the middle. In the middle, right? So it's easy to see with a pendulum, right? Because with a pendulum, you're just converting gravitational potential energy to kinetic energy and then back again, right? Okay? It's a little less obvious here, but the velocity does turn out to be the biggest here. This motion, though, is a lot more complicated because we don't just have GPE and KE. Sorry, we don't just have gravitational potential energy and kinetic energy. What other type of energy do we need to contend with? Elastic potential energy, right? Make sense? Okay. But the basic idea is at the midpoint, none of your energy is elastic. And so a larger percentage of your energy needs to be kinetic. Follow? All right. Now, all right, so these are stolen from your book. They are trying to help you understand how you, if you sort of imagine snapshots in time of your object oscillating, and then how do you translate that to a graph? All right, so remember, our original example that we were talking about was an example, before we did this example, we were talking about something oscillating horizontally, right? Okay. And so the idea here is, this is basically just showing you that at time zero, you're going to have some position, right? Our force is this way, so it's going to be accelerating this way. So, after some amount of time, it'll be back to the equilibrium point. After some other amount of time, it'll be at its, negative maximum position, etc. All right. Please make sure that you guys understand this is a really simple thing that you can do that'll come in really easy for you, or come in really handy for you. I was trying to say that. Time, position. So our graph is going to look, whatever, like, who cares? Sorry, I'm just trying to decide how I want to draw it. We'll keep it simple. So your graph looks like that, right? Okay. How much time did it take for my particle to get here? What's the name for that time right there? Period, right? So call this t, right? By that same logic, how much time did it take to get here? T over 2, right? And then to get here is t over 4, because it's half of a half. And then that means that this must be 3t over 4, okay? Please make sure you know that you're able to take a sine or a cosine wave and chop it up into quarters of a wavelength. Good? Please don't make this mistake. From here to here is not necessarily half of a, or even a quarter of a wavelength, right? Because it depends on how high up or down you are, right? Like that time is different from that time is different from that time. All right, and a lot of times people go, oh, well, they're going from the same point to the same point, so that's whatever, a quarter or a half, and you can't do that. Follow? Okay. Oops, I didn't mean to do that. So, I don't know how much else I want to say about all of this. I think this is all just kind of what we just talked about there. What's up?
Yeah.
Okay.
We thought the point was, never mind.
You sure?
Yeah, we understand it. He was explaining to me, and I was clarifying.
Okay, cool. All right, so this is the thing, oscillating in simple harmonic motion. We talked about the speed being greatest at the midpoint. We covered that. Rotating the figure gives you the wave. This is the graph of the motion. Yeah. All right, so let's go back to this again real quick. And then just identify these points here, the points that I just labeled with red dots, are important because those are the points where we have maximum what? Displacement, acceleration, and force, right? And then the points that I am now about to label with a green X are going to be the points with maximum velocity. Oh, maybe I shouldn't use an X, right? Because you're going to think that means X as X. How about if we use a green circle? We can just do a green dot. There we go. All right, so where's the maximum velocity? Here and here, right? Tell me why that's also true in terms of calculus. Okay, because cosine of 0 is 1, so that's your maximum sine, and that's where the graph is the steepest, right? Look, it starts out with a slope of 0, and it gets steeper, 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 and then, oh, it has to get less steep to curve the other way, right? Those are your inflection points, which is also why you're at maximum acceleration there. Cool? Very good. Questions? All right. All right. So these graphs are important just because they help you understand how changing one little property of your wave changes the way the graph looks. All right. So these graphs, the blue and the red graphs here, are identical except they have different amplitudes, right? They have a different XM, a different maximum position, right? Make sense? But in the same period, right? Okay. These graphs are the same except they have a different period, right? Or a different frequency, and a different frequency, right? And it looks to me like the blue one has twice the period of the red one, right? So I don't know if you guys can see, this is t, and these are t primes. So to me, it looks like t is 2 times t prime. That prime there doesn't mean derivative. It's just like, you know, they're recycling a variable. Yeah. Cool. All right, and then these guys are similar, except they have different phases, right? What's the technical name for that? That's an honest question. I'm so bad at vocabulary. Is it phase shift or phase constant? Somewhere it's in here. Phase constant or phase angle. That's what I was looking for, phase angle. Yeah, so they have different phase constants, different phase angles. You know, I keep wanting to say phase shift too, and that's wrong. All right, so and notice that the red one has a negative phase shift because it's been shifted to the right, resulting in a positive starting velocity, right? Good? Yeah. Cool. Also, I guess, notice that the phase constant on the blue one is 0, right? Because it's just a regular old cosine curve, right? Good? Is that the piece you were missing? I saw the light bulb. Cool? So yeah, maybe that's an important thing, you guys. Phase shift of 0 means your graph is just a regular old cosine curve. Good? Okay. All right, now, not so much with this system, but with a system that's oscillating horizontally. Did we play with this guy? I can't remember which class I played with this one. Can we do this? Maybe it was just my honors class I did this with. I was thinking I had done this with you guys too. All right.
We were playing over there.
Okay. Maybe not. I don't know. All right. So anyway, all right. So this is another example of simple harmonic motion. This one is actually simpler harmonic motion. than this one, because we only have two types of energy to contend with, right? This one has gravitational and elastic potential energy. This one, the gravitational potential energy is constant, right? Follow? Okay. At some point, we should probably talk. What do you guys tell me? So, we know the spring constant of these springs, right? Because this kind of spring is the same as this. So the spring constant was about 3 newtons per meter, right? How do you think we would deal with this, where there are two such springs? What does that do to the spring constant?
Double.
Yeah, exactly. Doubles it. Why? Yeah, because you're deforming two springs, right? So if I want to squish this thing this way a meter, then I'm stretching this one a meter and squashing that one a meter. So you're deforming two springs, so you need twice as much force to get the same distance, right? Make sense? Okay.
So those springs push back in their
They don't actually, but it turns out that it doesn't matter.
Why?
That was amazing. I'll tell you what. I don't want to spend time on it right now. I wasn't sure either, and I went through let me see if I can come up with a guided exercise to help you see why. I think that would probably be more valuable than me just showing you. All right? I'll see if I can throw that together tonight, and maybe you guys can work on that a little over the weekend. All right? Because I did go through the calculations, and it doesn't matter. And it's interesting. All right. No, now I'm just thinking about how that's going to work. All right. So anyway, all right, so what I was going to say then is, so anytime you're in simple harmonic motion, you're basically just exchanging potential energy for kinetic energy and vice versa, right? Okay? All of the problems I've seen in the book have been this. Okay? The only reason I didn't do this for an example is because I couldn't hook the motion sensor up to it. Okay? Because of the way the springs are set up. Okay? So that's why I did this. All right? But all of the examples I've looked at have been just horizontal. So all of your exchanges are elastic and kinetic. Yeah.
So when you're talking about the force on the cart, it's 2 times the K, right?
Correct. Yes.
But, and then are there questions where it's asking individual force? Does the other spring affect that?
I would, if I were solving this problem, I would treat this as one big spring
Okay.
with a spring constant of 2K.
Yeah.
Cool?
Yep.
And then I guess you certainly could, if you wanted to, then consider one individual spring, and you'd have to use just regular K then. I haven't seen anything like that, but there's no reason why you couldn't do it. Okay? All right. All right, so notice, so the idea, yeah. So over here we've got our maximum elastic potential energy. Over here we've got our maximum elastic potential energy. Oh, what was that an example of?
Gravitation.
4! Good answer. All right. So maximum elastic, which means in the middle we're at 0 elastic, and therefore maximum kinetic, right? Okay? So if you want to find the energy in your system, you've got 2 options. You can either consider the endpoints where all of your motion is, where all of your energy is elastic, right? Or you can consider the midpoint where all of your energy is kinetic. And as a result, to find the energy in our system, you can either find the maximum kinetic energy, right? 1/2 m times maximum velocity squared would give maximum kinetic energy. Or you can do maximum elastic potential energy, right? 1/2 kx squared. Remember, 1/2 kx squared is the equation for elastic potential energy. And I'm finding the maximum by using my maximum displacement. Cool? And notice the squareds tell you it doesn't matter what direction it's moving, right? Cool? All right, so the idea is, if I pull this back, whatever, 40 centimeters, and then let it go, based on that 40 centimeters, I can figure out how much elastic potential energy I began with, and therefore how much kinetic energy it has in the middle. You know, and if I pick an arbitrary position, I can find the velocity at that point. Cool? conservation of energy. That's what this problem is. All right. So make sure you understand that there are a lot of problems where you have to use conservation of energy to solve. Cool. All right. I have, I think, one more example that I wanted to do. I do, but we only have about 2 minutes, so we're not going to get through it. Let's see, what else do we have to do? Oh, shoot. All right, so we're going to have to do 2 more days. Darn it. Oh, well, no, maybe not, because this thing isn't a whole day. We probably have about another day and a half. All right, so Monday and Tuesday, we'll finish up those. Okay? Here's what I'm thinking. Some of you guys asked about a test for this chapter. I think I probably want to do a test on it, but I think I might wait till after the AP test. That way we can spend more time reviewing. So that gives you more grades and more time to prepare. I don't know, we'll see. Yeah.